Swayam Prabha. Digital India. Educated India.
So, we have 4 equations and 4 unknowns. So, let us look at them and try to solve. Okay. So, let me first show the first equation. You look at this, E u prime square by 2 plus lambda minus E lambda prime u prime equal to 0. So, let us first write that equation here. Equation 1, we have E u prime square by 2 minus lambda plus lambda, let us look at that, plus lambda minus E lambda prime u prime plus lambda minus E lambda prime u prime equal to 0. That is our first equation. Second equation is E a lambda prime whole prime minus E a prime u prime E a u double prime. In fact, if you notice these two terms, okay, actually are, I can write it as minus E a u prime prime, because if I expand this, E a prime u prime and E a u double prime we get. So, it is E a lambda prime prime minus E a u prime prime. Okay. If I write the second equation, which we call adjoint equation, okay, which is E a u prime prime, rather I think we had the lambda prime first and then u prime later. So, this one is E a lambda prime prime minus E a u prime prime equal to 0. Okay. And then equation 3, which is our complementarity condition, that is lambda times integral 0 to L a dx minus v star equal to 0, and the condition that lambda should be greater than or equal to 0. And a fourth one, which is E a u prime prime plus p equal to 0. These are our 4 equations. Now, one thing we notice over here, which is our adjoint equation, if you compare that with our governing differential equation, you see that they are of the same form. If you look at equation 4, it is E a u prime prime plus p equal to 0, and equation 2 is E a lambda prime prime minus E a u prime prime equal to 0. This part, okay, is called adjoint load. This is called adjoint load, okay, because if you look at this term and this term, they are the same except that u is replaced with lambda. For this one, this is the actual load, right, that is the given load, actual load on the structure, whereas this is called adjoint load. This equation helps us solve u of x. If somebody gives us E, A and P, we can solve for u. Similarly, this adjoint equation, we call this as adjoint equation. Okay. If somebody gives us the adjoint load and E and A, we can solve for lambda. So, using this we can solve for lambda x. In fact, here it is obvious to see, because we have two terms E a lambda prime prime minus E a u prime prime, that immediately tells us that in this particular case lambda x is equal to u of x. So, the displacement, axial displacement u of x is equal to lambda of x, which is the Lagrange multiplier function. Okay. Now, knowing that, if we substitute this result into 1, you put this result into 1, then what does 1 become? We have e u prime square by 2 plus lambda minus e lambda prime u prime is equal to 0. If lambda is equal to u, we also know that lambda prime will be equal to u prime. So, let us replace this lambda prime with u prime, right. Then we get u prime square here, right. Here we have u prime square by 2, here u prime square. Overall what we get now will be lambda minus e u prime square by 2 is equal to 0, or lambda is equal to e u prime square by 2. And this is an interesting result for us, because we can actually compare this with what we have about lambda. Look at that, we had said lambda should be greater than or equal to 0. That is exactly what we got, because E, which is Young's modulus, which is most often not negative, right. For a material, most material that we use in general will have E equal to a positive value. There are cases, very advanced cases, where you actually design a material, you can design materials, you can have a negative Young's modulus for a brief period. When I said not time, but a range you can have, but in general E is positive. E is positive, 2 is positive, u prime square is positive irrespective of whether u prime is negative or positive. So, overall we are satisfying this condition. In fact, now we can look at this complementarity condition, lambda times the volume constraint equal to 0. We want to know whether lambda is equal to 0 or the volume constraint part is equal to 0. Here we can see that, let us say lambda equal to 0, in which case the constraint is not active. Constraint not active meaning integral a dx minus v star less than or equal to 0 is not equal to 0. Instead of less than or equal is not equal to 0, it is strictly less than, then lambda is 0. If lambda is 0, what we find is that u prime is 0. When u prime is 0, you look at this equation, when u prime is 0, you take another derivative of it. If u prime is 0 identically from 0 to L, the whole thing is 0, but plus p should be equal to 0, but p is something that is given to us. So, we do not allow from here and the governing differential equation, we conclude that lambda is not equal to 0. If it is equal to 0, we would have, okay, if, let us write down, if lambda is equal to 0, okay, what we get is that from this equation, from that equation we say that u prime should be equal to 0. Then from this equation we will have 0 prime plus p equal to 0, which is not true because p is given to us. So, lambda is not equal to 0. When it is not equal to 0, it should be positive. So, we know that lambda should be greater than 0 in this problem. Okay. That is u prime everywhere should be positive. Anyway, u prime whatever it is, u prime square lambda we have, it is easy to see that this lambda is positive, and you also see u prime is a function of x, but then lambda is a constant. So, what it tells you from here, we conclude that u prime, which is equal to 2 lambda by e, okay, square root, and plus minus, it will be plus or minus both. Okay, let me clean that up a little bit. U prime is equal to plus or minus, because u prime square is there, I am taking square root. So, I should allow both plus and minus. In any case, what we have arrived at is that u prime is equal to constant, because it depends on capital lambda, which is constant, e which is a constant, and 2 which is a constant, right. U prime equal to constant. What does it mean? U prime for a bar which is du by dx is nothing but axial strain. If you recall the definition of the strain, change in length by original length. So, if I have a bar, okay, which is a bar of some cross section, if I take a section there, let us say this distance originally is dx. When this bar deforms due to actual loading, right, when the load is applied, it is going to deform, and if that is u of x, the function, du will be the displacement. Du is the displacement of that little dx. Okay. Du is the incremental displacement of dx element. Okay. So, based on the strain that we know very well, du by dx. If that is strain, okay, axial strain epsilon, then the stress is E times epsilon, that is E du by dx. Since du by dx is constant, stress is also constant. So, what we have here is a uniformly stressed design. Okay. Sigma equal to constant means that we have uniformly stressed design, uniformly stressed design. So, our optimal design here has the property that it is stressed equally everywhere. That actually makes sense if you think about it, because we are trying to minimize the strain energy subject to a volume constraint. Okay. Then in order to minimize strain energy, the material at every point in the domain 0 to L must contribute towards minimizing strain energy. And how can that happen? If you stress every point equally. If some part is not contributing enough towards minimizing strain energy, then that is not being fully utilized, right. So, uniformly stressed design here gives you the optimal thing. You go back and look at an example that we had taken, where we had taken this example in finite variable optimization, maximize the product x1 times x2, maximize the product x1 times x2, two variables x1 and x2 subject to the constraint that x1 plus x2 is equal to or less than or equal to 1 we can put, right. In this case, when less than or equal to, you might as well use up all of 1 that is given, that is you will choose x1 x2 such that their sum equals 1 and not less. Okay. So, if you, because you want to maximize the product of x1 x2. Okay. Now, if you see what is the answer for this, it will be where x1 is equal to actually x2. If you actually take different numbers, I write x1 and x2 and x1 x2 like in columns. Okay. If I say this is 1 and 0, because sum of these two should be equal to 1, that will be 0, and then I take this to be 0.9 and this is 0.1, this will become 0.09, and then I put 0.8, 0.2, each time making sure that I use up the resource, that is 1, this will become 0.16, slightly more, it is increasing, and then we have 0.7, 0.3, that will become 0.21, then 0.6, 0.4, that is 0.24, and then I have 0.5 and 0.5, that will be 0.25. So far that is a maximum. See what happens when I go to 0.6 and 0.4, then I get back down like these two. Next one 0.7 and 0.3, if we go, this is 0.7 and 0.3, that will become 0.21, just like this, symmetric. So, you see when these two are equal, that is when, because there is symmetry in this problem, there is no difference when you put material at one location or the another in this case, because we assumed a p of x that is given, that load is acting everywhere. If you want to get uniformly stressed. If you want to get the stiffest structure of a given amount of material, then you have to make it uniformly stressed. Okay. So, we have this feature of optimal design, that uniformly stressed design, and that is also fully stressed. Like we have to use up all the material, here we will use up all the material and make it fully stressed as well, then you get an optimal structure. Okay. In fact, this is just a qualitative feature. Optimal structures, not only this bar, when you take a beam or a plate or a continuous two dimensional structure or three dimensional structure, when you want to maximize the stiffness or minimize the strain energy for given amount of material, then you end up with this feature of uniformly stressed design. Throughout the structure, you should have equal stress and equal strain, and also equal strain energy density, meaning the stress strain curve when you draw, area under that, which will be half sigma epsilon, that will also be uniform throughout the structure. Okay. Now, let us go back to our equations. Now, we have solved lambda equal to u already, and u itself can be solved by solving the governing equation. Now, we have also found that a dx minus v star has to be active, meaning that should be equal to 0. So, lambda is greater than 0. We know what lambda is, and lambda is plus or minus square root of 2 lambda by e. We have done everything. Now, we need to solve, right. We can solve because we know u prime, which is over here, right. We substitute that into this equation, then we will be able to solve A. Now, we can see the design equation, right, that is what gave us u prime. That is what we started, design equation. Even though there is no A, it gave us the feature of optimality here, which is uniformly stressed design, and we got u prime and we substitute over here. Okay. So, into the governing equation, which is E A u prime plus p equal to 0, and we have u prime plus or minus square root of it was 2 lambda by e, right. Let us look at that, square root of 2 lambda by e plus or minus. We can take either, that depends on the kind of boundary condition that we will take, that will come later. For now, let us take positive sign. So, I can put E A u prime, I will take positive sign. So, I will put square root of 2 lambda by e and prime plus p equal to 0. So, what I get, this e in the square root over here that goes. So, what I get is 2 lambda e square root into a prime, because that is all constant, e is constant, lambda is constant, 2 is constant. This prime applies only to a plus p equal to 0. Okay. How do you find area? We simply integrate, right. So, I can write a prime is minus p into square root of 2 lambda over e, and I can integrate to get a, which is integral 0 to L minus p by square root of 2 lambda e, actually not definite indefinite integral here, okay, dx, okay, because a is a function, right. It is a we do not know at every point, plus some constant, right. If I integrate this, I will be able to find area of cross section, optimal area of cross section. Okay. Now, p of x is something that is given to us. If we know p, I can integrate. Let us take a special case, okay, of let p of x, it is actually a function that can vary whichever way you want, but let us take it to be some p0, some constant, that is everywhere we are applying the same force p naught, right. If it is constant, then from here we can see a will simply be integral minus p naught, it is not p of x now, just constant, and 2 lambda e under square root dx plus c. Okay. So, we can integrate this, right, just everything is constant, that will be, this implies a of x will be minus p naught x divided by square root of 2 lambda e plus c. That will be our area of cross section, okay, which is a linearly tapering down cross section, because this is just constant, okay, c is just some constant and p naught is constant, that is given to us, 2 lambda e are constant, we do not know lambda yet, but we can find it. How do we find? We have the volume constraint for it. Okay. So, if we go back to our thing, we have not yet used this constraint, equation 3. We only have concluded lambda should not be equal to 0 here and it should be positive, and we found the lambda value over here. We have not used this integral a dx minus v star should be equal to 0. If you put that, we can find lambda, provided to get the boundary conditions. When you do boundary condition, we know what c is. In order to find lambda, we would use the volume constraint. After this, in order to find lambda, we need to use 0 to L a dx minus v star equal to 0. So, lambda will contain this v star, substitute back, you already have expression, it varies linearly with a negative slope. Okay. We have the solution for the problem. Okay. Now, we have to look at the boundary conditions also in this problem. Okay. So, for that we have to remember what our integrand is, right. Integrand f that we have in this problem. In the Lagrangian, we had started with the strain energy, that was E A u prime square by 2, and then governing equation had these terms, which is lambda times E A u prime prime plus p, and then we had in the constraint lambda a dx. I am leaving out lambda minus v star, right. This is the integrand that we had. So, we can even look at that once, that we had written earlier to be sure, okay, all the way up where we had written this E A u prime over here, E A u prime square by 2 lambda times E A prime prime plus p plus lambda a. Okay, let us see if we wrote the same thing here, right. This is it. Now, in order to write the boundary conditions, when you take variation with respect to of the Lagrangian with respect to A, that is equal to 0, we had the Euler-Lagrange equation, which we call design equation, that is done. The boundary condition, in this case, this contains, again we have to expand this, let me do that. This will be E A prime u prime plus E A u double prime. So, we have A and A prime, both terms are there. In such a case, if you recall, our boundary condition was dou f by dou A prime into we had that h, okay, that variation, which I am just denoting with delta A now. This is this delta A is h, or the variation. Once we had put h a subscript, now I am just denoting that with delta A. So, this is delta A, which is h a, which is the variation of A, that is area profile, perturbing it a little bit, that at either end should be equal to 0. That was our condition. Here is where the importance of calculus of variations comes through. It is not enough just to know how to write Euler-Lagrange equations, we need to know the boundary conditions. In fact, later on we will find some more subtleties in calculus of variations, where we need to figure out how to write this properly so that we can solve any problem. Okay? This is dou f by dou A prime delta A 0 to L equal to 0. that in this particular case dou f by dou a prime, where is it? It is over here, right? That is the term that has a prime, that gives us lambda e u prime, that will be dou f by dou a prime times delta a at either end should be equal to 0. Again we also know that lambda is equal to u in this problem. So, this becomes u e u prime times delta a at either end should be equal to 0. So, first let us consider at x equal to 0 and then consider x equal to L. Okay. Now, we need to talk about boundary conditions. So far we said just a bar. A bar's boundary condition can be free, it can be fixed free or free fixed. Let us take the bar that we are trying to design to be a fixed free bar. I do not know area profile, so I am not drawing it. So, I say this is fixed here and then free there. Okay. Now, if you look at this x equal to 0, u is equal to 0, right. So, it is satisfied. This boundary condition is satisfied because u is specified, that is 0, right. And let us look at the right end. At the right end, u is not 0 because that is free. What about u prime? In fact, the boundary condition from the governing equation here would tell you that u prime is actually also equal to 0 there, because that is a natural boundary condition, Neumann boundary condition. So, if when a bar is free, if you write the boundary conditions for the governing differential equation along with that, you would say that u prime at x equal to L is 0. So, this boundary condition is satisfied, alright. So, there is nothing much that we need to know over there, right. Now, if we go further, again I would need this integrand, write it again here for the boundary condition to take various with respect to u. This is E a u prime square by 2 plus lambda E a prime u prime, that is the first term, that is over that, and then we also have lambda E a u double prime plus lambda a. I am just writing for convenience. As we go down to the next thing we can write. Now, here we want to write Lagrangian derivative with respect to u, right. Then we get what we called adjoint equation, which we already dealt with, Euler-Lagrange equation plus our boundary conditions. Okay. Those boundary conditions will be this. So, that one will be dou f by dou u double prime into delta u prime is equal to 0. Okay. And we have the next one, which is dou f by dou u prime minus dou f by dou u double prime prime, this whole thing times delta u at either end should be equal to 0. There are two sets of boundary conditions, two boundary conditions. I say sets because they have to be valid at x equal to 0 as well as x equal to L. Okay. Now, let us write them down by looking at this f there. So, what does this tell us? This one dou f by dou u double prime, where is it? It is over here. So, that gives me lambda E a, right, that is it, times delta u prime at 0 L should be equal to 0. Also note that this lambda here is nothing but u, right, that is what is true. So, x equal to 0, u equal to 0, it is satisfied, u is equal to 0, we satisfy the boundary condition. Now, at the other end, right, where we have at x equal to L, u is not 0 because it is free, E is of course not 0, and delta u prime is also not fixed, because u prime that we have there is when it becomes 0, it is like a Neumann boundary condition or natural boundary condition, we are not specifying it. There we say A must be 0. So, this one, in order to satisfy, we conclude that A at x equal to L should be equal to 0. A at x equal to L should be 0 in order to satisfy this boundary condition. Okay. That makes sense, because we already saw that area profile is tapering down. When it tapering down, we say it should become 0, that is we specify. When I say over here A should be equal to 0, it just happens, unless you put another constraint that A should not become 0. Okay. For now we have no constraint, A can become 0 to satisfy this, all right. Now similarly we can write for the next one, right. So, this F is there, this is done. We got something interesting what we need there, all right. So, here we, if we write the second one, dou F by dou u prime, that will be E A half, and that goes, will become u prime, and then minus the second part will have lambda E A prime, and then prime of this, that is all we have, and then that times delta u is equal to 0. Again we know that lambda is nothing but u. So, we will have E A u prime minus u A e prime that will give us. So, this particular thing is E A prime and then prime, we will take derivative. So, I will have u prime A prime E minus u E A double prime, okay, this whole thing into delta u equal to 0. Now, we have this is A prime, anything gets cancelled, E A u prime A prime E, they do not get cancelled, but you can see what happens at x equal to 0 and x equal to L, and find out how this condition can be satisfied. When x equal to 0, if we look at it, we have delta u. Delta u means that if u is specified to be 0, delta u is 0. So, at x equal to L, x equal to 0, we have no problem, this is automatically satisfied because that is equal to 0. At the other end, x equal to L, u prime is 0, that is gone, and u prime here, that is gone, and then you have E A double prime. So, for that to be because delta u is not 0 at the other end, this should be 0, E is not 0, A is 0, A double prime should be equal to 0, which we have because we got A to be linear profile. When you take one derivative it will be constant, second derivative I take it is 0. So, that is also satisfied. So, both this end and that end, these are satisfied. What we got out of that is this thing, A equal to 0. So, if I were to go back and say what my area profile for this case is, we got minus P naught x divided by square root of 2 E lambda plus C was there, right. Now, we got the condition that since A at x equal to L equal to 0, then we can find C. What happens? Then it will be P naught L by square root of 2 E lambda plus C equal to 0, that will be C. So, that gives us C equal to P naught L by square root of 2 E lambda. Okay. Once we have this much, then we can go back to our volume constraint 0 to L A dx equal to 0, then sorry, that is not equal to 0, that is minus V star equal to 0. Then we substitute this A that we got, which is integral 0 to L minus P naught x divided by square root of 2 E lambda plus C that we just got now, P naught L by square root of 2e lambda dx is equal to v star. From here we can get this lambda. You substitute there, you get the answer. But qualitatively we already know that it is a linearly tapering profile. If I say x equal to 0 to x equal to L, here area profile, that is what we want, is 0, and then linearly tapering, it will go something like this. At x equal to 0, if you look at our expression for area of cross section, C is there, this part goes, it will be C. So, that value there is going to be P naught L by square root of 2e lambda, and the volume you integrate A dx, whatever that is area under this should be equal to V star, and that gives you the value of this lambda. Okay. So, we have solved the problem completely including the boundary conditions for a special case of P being equal to P naught constant. What if P is some arbitrary thing? Let us say I say P naught is given like a arbitrary function. So, P of x here is not constant as we assumed, but let us say it is something like that from x equal to 0 to x equal to L. Then we have to integrate and do it for different boundary conditions. We have to we have boundary conditions already, we have to make sure that everything is satisfied, impose them and try to get that, which we will consider in the next lecture.